Hi guys, this is Miss Scott. So today we are going to look at all of the theorems in chapter 5. Um, this is kind of just going to be using pictures, so um, use this as kind of just a quick recap of everything we've learned in chapter 5. Alright, so the first theorem deals with what we call a mid-segment, so we're going to put the midpoints here. So if these are the midpoints, we know they're right in the middle of each segment. And then we're going to draw a line there. So I'm just going to remind myself that this here is what we call a mid-segment. And let's say that it's x units long. Well, if that mid-segment is x units long, then we know we can take that length and double it to get the side across from it. So if it was like 3 units long, the side across from it or parallel to it would be 6 units long. If it was 4, it would be 8, and so on. All right, so let's look at another theorem here. The next one tells us that if we have a point, so let's call this point A, this point B, and this point C, and then say that point is on the perpendicular bisector of this line. Well, if that's true, then we know that point C is equidistant to these 2 points A and B, so that this distance here is the same as this distance here. All right. 5.3 is actually just the converse of that theorem, so we're going to start with the fact that point C is equidistant to A and B. So if that's true, point C is on the perpendicular bisector of segment AB. All right. So this is just the converse of that theorem. So these are kind of connected here. All right, let's look at theorem 5.4. So theorem 5.4 tells us that if we have the circumcenter, so if you remember, the circumcenter is created by the perpendicular bisectors. So this is just a rough sketch, but we're going to do our best to draw the 3 perpendicular bisectors here. And if that is so if you have the circumcenter, remember that that point is the same distance to the corners. So we're going to redraw that same thing again. And that point is equidistant to each of the sides, or each of the vertices. All right. And I'm having a rough time doing this. Okay, let's try again. So from the middle to the opposite corner, and then from the middle to the opposite corner. All right, so this point here is the same distance to each corner. So it's equidistant to the vertices. All right. And then theorem 5.5 is a little bit different than that. 5.5 tells us that if you have a point on the angle bisector, so here's the angle bisector, and if I have a point somewhere on that angle bisector, then that point, so that point on the angle bisector, is equidistant to the sides of the triangle. So these are the same length. All right, theorem 5.6 is the converse of that. All right, so move this down a little bit. All right, so 5.6 starts with, you know that a point, so say that this point is equidistant to the sides, then you know that point is on the angle bisector. So what you can do is, starting with that same picture, you know that this angle has to be the same degrees as this angle, all right? So you need to know that those are equidistant to the sides. All right, let me zoom in a little bit so we can see this next one here. All right. The next one deals with the incenter. So if you remember, for the incenter, we need to have the angle bisectors. So let's make all three of those. So we have this angle bisector, we have this angle bisector, and then we have this third angle bisector. So this right here is the incenter. And the incenter is not the same distance to the three vertices, it's the same distance to the three sides. So if we have the incenter again, so I'm just going to redraw that. All right. So if we have the incenter of a triangle, then it is equidistant to the sides. So the distance from that point to this side, from that point to this side, and that point to this side are all the same. And that's if you have the incenter. All right. Okay, let us move on to Theorem 5.8, which deals with the centroid, which remember is the center of gravity. Okay, so the centroid is found by finding all the medians. So if you recall to find the medians of a triangle, let's do this in orange, we need to find the midpoint of each side. So here's the midpoint of this side, and then we connect from the midpoint to this corner. Here's the midpoint of this side, so we connect from there to the opposite vertex, and then here's the midpoint of this side, so we connect from there to the opposite vertex. So this point in the middle is what we call the centroid, or the center of gravity. Then what we know about that point, so let me redraw that really quick here. So what we know about that point should be, so here's a midpoint, here's a midpoint, and here's the third midpoint. So that point, it turns out, does this. It divides, so if you know that this part here is x, this longer segment is 2x. And you can use numbers for that, so like say that this little piece was 5, this longer piece would be 10, and the whole thing would be 15 units long. All right, that's for the centroid. And then the last point of concurrency that we talked about was the orthocenter, which, if you recall, doesn't really have any special characteristics, but we'll just put it on here anyway. So the orthocenter is found by finding the altitudes or the heights with respect to each side. Oops, this should be straighter. So there's the altitude of that side and the altitude of this side. And I'm just going to call this point O here. Then O is the orthocenter. So there's not really any special characteristics about point O other than we call it the orthocenter. All right, so we're not going to spend a lot of time on that one. Okay, Theorem 5.10 deals with what we call, that's when we compare the sides and the angles. So say we've got a triangle, and in this triangle, we know that, say this side here is 9 units long and this side is 10 units long. And let's call this angle A and this angle B. Well, we know that 10 is bigger than 9. So if that's true, the side or the angle across from 10, so the measure of angle A has to be greater than the angle across from the 9, which is the measure of angle B. Okay, So that's what we were talking about when we're talking about included angles across from certain sides. Okay, let's get rid of this. Theorem 5.11 is the same idea, but now we know the angles. So let's suppose this angle here is 40 degrees, and this angle here is 45 degrees, and let's call this length over here C, and this length D. All right, so again, let's look at this. We know that 45 degrees is greater than 40 degrees. Well, if that's true, side C is across from the 45, so C has to be greater than the side across from the 40 degrees, side D. All right, and then we can kind of summarize that with all three sides. So this is what we talked about in section 5.5. If we have, say, triangle ABC, then remember any two sides has to be longer than the third side. So if you add side AB and side BC, those two have to be greater than side AC. So these two sides have to be more than this third side. And that works with any combination. It just depends on which two are the smallest is what we usually look at. So it also has to be true that side AB and side AC have to be greater than side BC. So these two sides have to be greater than this side. And lastly, side AC and BC have to be greater than side AB. So these two sides have to be greater than this side. So any two sides have to be greater than the last side. Okay, and then in the very last section, we talked about the hinge theorem and its converse. So the first one here is the hinge theorem. So I'm just going to put a reminder here that this is called the hinge theorem. And what that tells us, say we've got this angle here, and say it's 40 degrees. Then we have this angle over here of 45 degrees. And if this side corresponds to this side, and over here in this triangle, these two are congruent, we can make a comparison about the sides across from those angles. Since we know that 40 degrees is bigger than 45 degrees, or is less than actually, so let's write it this way, 45 degrees is greater than 40 degrees, right? Well, that means the sides across, so in this case, A and B has to be greater than A. And on the other hand, the hinge converse starts with knowing the sides. So now let's call this angle A and angle B right here. Still, these two sides are congruent and these two sides are congruent. And if you know this is 9 units long and this is 10, since 10 is greater than 9, we can conclude that the measure of angle B is greater than the measure of angle A. And we just call those the hinge theorem and the hinge theorem converse. All right, so I hope that was a good way to recap a lot of the ideas that we looked at in chapter 5. Make sure you get this filled out because you can use it on your test. If you have any questions on anything here, let me know. But this is going to be very helpful when we start looking at some examples using variables and numbers. All right, thank you guys for watching, and we will see you next time.